Hi, this is the video presentation for our paper, Structural Patterns in Generative Models of Real-World Hypergraph. Hypergraph is an extension of graph, in which each hyperedge may contain an arbitrary number of nodes. Hypergraph can be used to model various types of interactions that we encounter in real life. For example, if a node is a researcher, then a paper publication can be regarded as a hyperedge because that publication is a result of the collaboration of several researchers. And if a node is an email, then a hyperedge can be a list of recipients of an email address. In a similar context, if we treat each tag representing a subject as a node, then a discussion forum involving several subjects can be regarded as a hyperedge. So the main goal of this research is to establish a set of common patterns as well as the underlying mechanisms of the real-world hypergraph. The freedom in the number of nodes naturally leads to the complexity of hypergraph. Due to the complex representation and lack of existing tools, hypergraph is not straightforward to analyze. A conventional method to deal with this is the projection, which represents a hypergraph as a pairwise graph, in which two nodes are connected if they are invoked in the same hyperedge. However, this representation fails to represent the higher order level interactions, and it also incurs some information loss, as we cannot recover the original hypergraph from the projected graph. In order to address this issue, we introduce our decomposition tool, which represents each hypergraph as a set of pairwise graphs. By this representation, we can leverage the existing tools for pairwise graph to analyze the decomposed graph. Additionally, this representation does not incur any information loss, as we can construct the original hypergraph from the decomposition. This is an illustration for our decomposition tool. Let's consider a hypergraph having 4 hyperedges: 1, 2, 3, 4, 3, 4, 5, 5, 6, and 1, 7. In the most elementary type of decomposition, the node level, two nodes are linked if they're invoked in the same hyperedge. So as you can see, for the hyperedge 1, 2, 3, 4, in the node level decomposed graph, the hyperedge will be decomposed into a clique of size 4 involving 4 nodes: 1, 2, 3, 4. In order to reveal higher order level interactions, we also introduce the edge level decomposition, in which each node represents a subset of 2 nodes. And similarly, for 2 nodes, if the union is invoked in a hyperedge, then the 2 nodes representing the 2 subsets will be connected. So the hyperedge 1, 2, 3, 4 will result in a clique of size 6 involving 6 nodes: 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Next, we have the triangle level, in which each node represents a subset of 3 nodes. And with a similar explanation, the hyperedge 1, 2, 3, 4 will be decomposed into a clique of size 4 involving these four nodes: 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. And finally, we have the focus level, in which each node is a subset of 4 nodes. So in this case, the focus level decomposed graph only has an isolated node representing the subset 1, 2, 3, 4. By such explanation of decomposition, let's say we have a hypergraph in which the hyperedges are of size up to n. The decomposition will represent the hypergraph as a set of pairwise graphs up to the level of n-1 clique. This set of pairwise graphs can be analyzed quite conveniently because we can leverage the existing tools of pairwise graph. Besides, The decomposed graph can be used to reconstruct the original hypergraph, as our decomposition does not incur any information loss. In this paper, we investigate 13 datasets across 6 domains: email, drug component, drug use, online text, online thread, and co-authorship. The hypergraph datasets vary in terms of the number of nodes, the number of hyperedges, and the size distribution of the hyperedges. However, they share the same set of common patterns. Investigating this real-world hypergraph dataset, we consistently find 5 structural patterns that are evident in all decomposition levels: habitual degree distribution, giant connected component, high clustering coefficient, small effective diameter, and habitual singular value distribution. Here are the details for the first pattern, the habitual distribution. A distribution is said to be habitual if it decays at a slower rate compared to the exponential distribution. Roughly speaking, in this distribution, there are many samples with low values, whereas it is very rare, but there are still a few samples with high values. Intuitively, if we plot a habitual distribution on a log-log scale, the plot often approximates a straight line going downward. To confirm that a distribution is habitual, we employ 2 statistical tests. The first one is the Lilliefors hypothesis test, in which the null hypothesis is that the investigated distribution is exponential, while the alternative hypothesis is that the distribution is not. If the null hypothesis is rejected, we have evidence against the distribution being exponential. In our dataset, in most cases, the null hypothesis is rejected at the 2.5% significance level. Additionally, we also use the log likelihood ratio test, in which the test statistic is the log ratio of the likelihood of a habitual distribution denominated by the likelihood of the exponential distribution. If the test statistic is positive, it indicates that the distribution is more likely to be habitual than it is exponential. Next, the property giant connected component means that a large proportion of nodes are involved in the largest connected component of the graph. This property implies the connection within the graph. For clustering coefficient, we use the definition of the average of the local clustering coefficients. The local clustering coefficient at node I is defined to be 2 times the number of triangles involving I denominated by the number of wedges or open triangles involving I. For a graph to have a high clustering coefficient, it means the high tendency for 2 nodes sharing a same neighbor to be linked by an edge. Regarding the diameter, we use the notion of 90% effective diameter, which is defined to be a distance d by which 90% of the connected pairs are reachable within a path of length at most d. If a graph has a small effective diameter, it implies that most of the connected pairs can be reachable from each other within a small distance. Our hypothesis is that for a real-world hypergraph, in the decomposed graphs, the 5 structural patterns are satisfied. Here is the intuition why. So real-world graphs are often found to exhibit the 5 structural patterns: habitual degree distribution, giant connected component, high clustering coefficient, small effective diameter, and habitual singular value distribution. Let's consider a hypergraph. If we decompose it into the decomposed graph, the edges in each decomposed graph represent the relationship in a very similar manner to a real-world graph. For example, if we have a publication hypergraph, then the decomposed graph represents the co-authorship network. Or if we have an email hypergraph, then the decomposed graph represents a network within a company or an organization. Because these decomposed graphs represent the relationships very similar to the real-world graph, we suspect that they also exhibit the 5 structural patterns that are common in the real-world graph. Applying the linear force and the log likelihood ratio test, we found that the degree distributions in the decomposed graph of the hypergraph are heavy-tailed. The same observation can also be made here. The distributions of singular values in all decomposed graphs are also found to be heavy-tailed. For the giant connected component, the table illustrates the proportion of nodes involved in the largest connected component. The red numbers indicate that in that level of decomposition, the graph no longer retains a giant connected component. As you can see from the table, the level of decomposition up to which the graph retains a giant connected component varies among datasets. For example, in the co-authorship dataset, it's usually only up to the edge level, while at the tag dataset, the graph have a giant connected component up to the foregrip level. If there is a giant connected component in the graph, the clustering coefficient has been found to be high, and the effective diameter has been found to be small. What could be the underlying mechanisms for the real-world hypergraphs? Motivated by this question, we propose our model, HyperPA, which is an extension of the preferential attachment model, accounting for subset interactions. The main idea behind HyperPA is that subsets of nodes should get grouped together. To see how HyperPA works, we consider this example. Suppose we need to grow a hypergraph, and we already have 2 hyperedges, 1, 2, and 1, 2, 3. We maintain the degree for each node and each subset of nodes. And the degree for each subset is equal to the number of hyperedges containing that subset. So as you can see, node 1 and node 2 both have degree 2, while node 3 has degree 1. For the subset 1, 2, it has degree 2 because there are 2 hyperedges containing it. For both subset 2, 3 and subset 1, 3, their degree are both 1. And because there's only one hyperedge containing the subset 1, 2, 3, its degree is computed to be 1. Now, HyperPA will repeatedly grow the hypergraph by introducing new nodes and new hyperedges. Suppose here a new node arrives, node number 4. It will first determine the number of new hyperedges that it will form with the existing nodes. And in this case, node 4 will form 2 new hyperedges. The size of each hyperedge will be sampled, and will be sampled from a predetermined distribution. And in this case, for the first hyperedge, the size is sampled to be 2. So node 4 needs 1 more node to join the new hyperedge with. It considers all single nodes and takes into consideration the degrees of the nodes. The chance for a node to be chosen is proportional to its degree. So as you can see, node 2 is chosen, so we have a new hyperedge 2, 4. For the second hyperedge, the size is sampled to be 3. So node 4 needs to choose 2 other nodes to form this new hyperedge with. It looks at all subsets of 2 nodes, and again, the chance for a subset to be chosen is proportional to its degree. In this case, the chosen subset is 1, 3. So we have a new hyperedge 1, 3, 4. Once that is done, HyperPA adds the newly formed hyperedges to the hypergraph. So we have 2 more hyperedges, 2, 4, and 1, 3, 4. Then it updates the degrees of all subsets of nodes. Now we have 3 more subsets of 2 nodes, 1, 4, 2, 4, and 3, 4. We also have one more subset of 3 nodes, 1, 3, 4. Their degrees are updated accordingly, equal to the number of hyper edges containing them. Then we introduce a new node, node number 5, and repeat the selection process in a similar manner until the hypergraph reaches a predetermined number of nodes. With such mechanism, HyperPA is demonstrated to reproduce the 5 structural patterns of the global hypergraph across various decomposition levels. To show the role of subset interactions in reproducing the structural patterns, we consider a baseline model referred to as naive PA. Naive PA is a naive extension of the preferential attachment model. Instead of considering subset interactions, naive PA only maintains the degrees of nodes individually. And when choosing nodes to form new hyperedges, the nodes are chosen individually based on their degree. As you can see, different from HyperPA, naive PA disregards all subset interactions. With such mechanism, naive PA often fails to reproduce the 5 structural patterns. This illustrates the essential role that subset interactions play in reproducing the 5 structural patterns of the real-world hypergraph. In conclusion, our contributions are threefold. First, we introduce our decomposition tool, which represents each hypergraph as a set of pairwise graphs. This facilitates a convenient analysis and the reconstruction of the original hypergraph. Secondly, we establish a set of 5 structural patterns that are evident in all decomposition levels of the real-world hypergraph: habitual distribution, giant connector component, high constraint coefficient, small effective diameter, and habitual singular value distribution. Finally, we propose our model, HyperPA, which is a simple hypergraph generator capable of reproducing the 5 structural patterns of the real-world hypergraph. Thank you very much for attending our presentation. We hope you have a good time at KDD 2020.